Welcome to our today's webinar. The topic is Next Level Production, Additive Manufacturing as a Competitive Advantage for SMEs. This webinar is held in context of our project Manufacturing NextMaterials. But first of all, I would like to give you an overview about the agenda of today. We have a short introduction of Manufacturing NextMaterials because we think that it might be interesting for you to know how you can participate in this project. And in the main part, we will have one of our lighthouses presenting additive manufacturing. And afterwards, we will have a Q&A session. So if you have any questions, you can put them into the chat if you want, if you prefer. Or otherwise, you can raise your hand during the Q&A session, and then you can start a discussion. Okay, but first of all, I would like to start with Manufacturing NextMaterials. So as already mentioned, this is our project in the Interreg Deutschland-Nederland funding scheme. And what is it about? Our focus is on materials and technologies. So we focus on materials for energy generation, distribution, and storage. So energy materials in any case, even housings of batteries, for example. We have optics, ceramics, high-tech metals and coatings. Smart materials, modern textiles, and composites materials, and any other material, I would say, nearly. So therefore, I would say we have a very broad scope. But more interesting for you might be, how can you benefit from M&M? We would say there are different possibilities. As I already mentioned, you can, within M&M, Manufacturing NextMaterials, you can start your own project. You need to have two partners across the border. So you need a partner from the Netherlands and the other one from the funding area in the German part. We have workshops and trainings. Like today, we can provide matchmaking. So if you have an idea, but you are still don't have any clue for a partner, you can ask us. And we are also doing interviews to help to shape the lighthouses, but more on the lighthouses in the next step. Yeah, this is what I already mentioned. You can start your own project. And if you think about what could be such a project, we have some examples of the projects we already started with in M&M. It's, for example, Composite 3D. It's metallic composite granulates for advanced 3D printers. We have a project which focuses on the design innovation of unique 3D metal printed catalytic reactors for air purification. We have a consortium which develops a dual-armed robot, new dual-arm robot solution that combines additive and subtractive manufacturing. Also a new approach in a certain way. Hydrofoil production for lightweight, especially for maritime components, and also additive manufacturing for demanding industries with metallic components, high requirement sectors like oil or gas industry, maybe also aerospace or defense. Yeah. What are these projects? So the SMEs that participate in this open part, which we are talking about, you will receive a maximum funding rate of 50% for at least 50,000 euros or at max 70,000 euros per sub-project. The projects need to be completed by August 27, can also be earlier, and only personal costs are eligible. And what also might be interesting for you, but we will repeat this at the end of the webinar. The next call will close on 16th of January. So maybe it's a nice task for the holiday season to write a proposal. But the second pillar where you can benefit from are these workshops and trainings. And as I already mentioned, these are held by lighthouse projects, which are part of the closed part of this project. There we have 3 lighthouses, next thermoplastic composites production solutions. We have advanced solutions for battery materials. And today we are having this webinar with the distributed additive manufacturing. That's a pilot line for the scale-up of application of high high-speed 3D printing technologies, also for energy materials or spare parts, for example. And with this, I come to our topic today, the next level production, additive manufacturing as a competitive advantage for SMEs. Our speaker today, not me, but the more important speaker, is Dr. Stefan Klischinski. He is the academic Rat, I don't know this in English, I'm sorry for this, of the Rapid Technology Center of the University of Duisburg-Essen, which have the lead for this distributed additive manufacturing lighthouse. So, Stefan, I would say I stop my presentation here. You can start your sharing and the stage is yours. Thank you.
Okay, yeah. Thank you very much, Henry, for the kind introduction. You will see my slides, I think, right now, right?
Yes, perfect.
Okay, perfect. Yes, so our Lighthouse project is on distributed additive manufacturing, and I want to give you a short insight into what we are doing there and what we see as a challenge, mainly for SMEs in this context. I think everybody might know additive manufacturing or 3D printing. This kind of technology offers a lot of potential, but there are still a lot of challenges, especially when it comes to serial production and scale up and new materials and demands from the application. And these are all topics that we are focused on in our research activities. And to get a better understanding of what you need from the SME side, from the industry side, it's always important to get in touch with the industry, and therefore we like this project architecture and also the possibility to get in touch with you by this webinar and the upcoming workshop that we are planning for February next year. So, but before I start with introducing you into what we do in this project and what we could offer from the project side, I briefly want to introduce ourselves. We are the chair of Manufacturing Technology in Duisburg, and we have a long history in additive manufacturing. Our former professor, Gerd Witt, was one of the first German researchers and professors who was involved in the research and development for additive manufacturing. We're doing this now for more than 20 years, since 1989 and 1998, sorry. And that's why we have quite a good infrastructure and in our lab for doing this research on different scales, on different TRL scales, basically. So we are having some machines which are also used for industry manufacturing purposes. So we are dealing with different technologies. So we are processing metals and also polymers, and we are doing this with different additive manufacturing technologies. So we have powder bed fusion technology in-house. There we have 4 powder bed fusion machines who are suitable for processing polymers. We have 4 more machines who are able to produce metals and to manufacture metals. We are doing some research on material extrusion technologies. These are the kind of additive manufacturing technologies that you might know as FLM or FTM. And other terms for powder bed fusion are laser sintering or laser beam melting, selective laser melting. You might know that there are different terms for the same things. So there's a lot of confusion for sure in this community of additive manufacturing. But anyway, that's how it is, and that's basically how it's now standardized in the official ISO standards. And this is what we do for industry partners. We are offering capacities and capabilities to research on certain material systems or to design a process or to optimize a process for different applications that you might have in mind. What you also like doing is to do fundamental research. So this is a research activity where we are modifying existing AM systems or even where we build our own laser sintering systems. This was one nice project with a big industry consortium. And we are developing solutions for process monitoring. We have suitable lab equipment for doing the analytics, for analyzing the mechanical properties, but also the metallurgical properties. We are developing new devices for process heating, for process monitoring, simulation and stuff. And basically what you like doing for fundamental research, we have the DFG, which offers us a lot of funding, but also we like doing Interreg project, but also funded project by the German ministries. Yeah, and basically the motivation for the Lighthouse project that we have, the distributed additive manufacturing, is basically that we see some challenges for SMEs and for the industry in using additive manufacturing. For sure, it has to be economically efficient. So we need to find processes and also products and applications where this all makes sense in terms of euros, basically. So there's a lot of growth, a lot of confidence in some sorts of additive manufacturing, but for sure, it's not easy to meet the properties that we are looking for, and also maybe there are some also struggling with the reproducibility and the quality of the parts that being produced. So this is one topic that we see does really affects the economic efficiency of the process chain. And one other thing is approaching. I think most of you might have already a feeling for this. The energy costs are exploding. So additionally, there's more focus on sustainability and the usage of circular economy approaches. So, but therefore, we have for sure some experience using circular materials, the polymer processing, for example, when it comes to the PET bottles that everybody knows. We have working circular systems, but this is not the case for any polymer that we are using. So maybe there's a need for developing new circular materials and to think about new process change that might improve the sustainability of production. And in combination with processes that are efficient in a way that we only use the materials that we are basically needing for the component, this is something that might be possible with additive manufacturing. So we can have an impact on all these three columns, the economic efficiency, the sustainability, and for sure also the energy related aspects for manufacturing and production. So our opinion is that additive manufacturing might help to overcome these challenges, and we have to see the bigger picture here. It might not only have, if you have a system in your facilities and if you have a single printer, that's good, but if we can join our forces to develop something like a production network, which is then decentrally organized, maybe, we have the possibility to go for something that we like to call the distributed manufacturing. So if the location of the production site is close to the point of consumption, this might bring some advantages. We could be able to shorten the supply chains. And I think this is something that everybody really noticed during the pandemic. There was a time where it was really hard to get the simplest things. All the supermarkets were empty, and basically this was why the reason was that the global supply chains was heavily distorted by the pandemic, and unfortunately there are a lot of different other crises around the world. So this might not be better in future. So it might be intelligent to develop more capacities for locating the production closer to the site of consumption. And this, as an additional advantage, we are able to be more agile in our supply and process change. We can keep the production here in the country, in the European Union. And the other advantage might be that we might be able to reduce the emissions and also maybe the energy consumption, the material consumption. So this might be a chance to develop strategies and to build up capacities for processing new and eco-friendly materials that are also able to be circular. So this is one thing. And the other thing that we see, we are in touch with a lot of different other researchers who are doing research on hydrogen technology, on fuel cell technology. We have a big fuel cell technology center here in Duisburg, right next to us. And so the idea came up, all right, when we are able to build up this agile and distributed production network, maybe we can also look for tailored new materials who might then also be interesting for such new approaching technologies like the hydrogen technology. It's not really new. This fuel cell center exists for more than 20 years, but for sure in the last years, the relevance was a bit enhanced by all this crisis that we had during the last year. So this was one idea that built up our motivation to take a look at new and promising materials for energy applications, basically. So, and I think most of you might know the potential and the advantages of additive manufacturing. So we have this toolless production. These are processes and production chains that are really strongly digital. So we have always a digital process approaching. We need to prepare CAD files, and we have to do the pre-processing of the process, so the preparation of the process parameters, but also the preparation of the part geometries is necessary here. And this is also one reason why additive manufacturing is close related to the Industry 4.0 strategy. And this is widely known. So also the German Bundestag knew it. They highlighted the potential in the coalition contract recently. So there they stated that additive manufacturing is important for Germany, but also for the European Union. And also, as Biden used to be president, he once made a tweet where he also stated that 3D printing or additive manufacturing is a strong method to reduce the lead time for production. And so there was a lot of funding in the US for additive manufacturing. Also in Asia and China, there's a lot of funding for developing new production capacities by additive manufacturing. So, but what we do notice here still is that most of the SMEs that we know are struggling a bit because there's a missing infrastructure, and for sure these are processes and production capacities or capabilities that not everybody knows in every detail. There has been a lot of development in the last 15 years. We see it by taking a look into the market reports that we know. The good news is that there's a strong and increasing market, which is still growing. Expect especially from 2020 on, where all this crisis started. So we have still growing market values here, but there's for sure also a really highly dynamic development of the technology. And that is one reason why not everybody knows everything about every process detail on additive manufacturing. And a lot of research activity is still going on, which is good for us as a researcher. But I think that is maybe not so an advantage for the SMEs and the industry guys who want to know what's going on and how to tailor a process to be economically efficient in the end. So there's a need from our side, and we see that we might help here because we are doing research for a long time now on this topic, and we are involved in a lot of ongoing research activities on different TRL levels. And we see that one important thing, what we noticed in the past, is that most of the SMEs in our industry partners need some assistance in what we call part screening. So you need to know exactly when additive manufacturing makes sense. It doesn't make sense for standard parts that you can easily produce by forging technologies or by other forming technologies. You need to have some key characteristics for the parts that you want to produce with additive manufacturing. And one thing that works quite nice is spare part production. So we are able to produce spare parts only on the basis of existing digital product data. So if you might have a CAD file from your spare part in stock, so on your PC or wherever, and you have the infrastructure for printing the part, you might be able to produce a spare part in days or maybe in hours instead of months. So, and this could be a big advantage if it comes to big facilities or big machines who are not able to run because the spare parts are not available. So we want to offer a possibility to explore the possibility for you to see how you might be able to produce spare parts for your own purposes, but also maybe for your partners that you are cooperating with. So, and this is there's a lot of already known methodology for finding the spare parts. So some colleagues from Roland Berger summed this up. Basically, you need to filter, to screen for the parts. You need to prioritize which parts should be a spare part for additive manufacturing in terms of costs, for sure, in terms of other key properties that you define. Then you have to select the technology that you are using for the additive manufacturing. Also, the material selection is important here. And then basically, it should be the main goal then should be to go for something like a digital warehouse, basically. So, and we are not the only guys who think this is a good idea. A lot of other colleagues already did this. We presented here some use case examples. So some colleagues from Deutsche Edelstahlwerke, they produce a spare part like this. It was a lightweight design. So it used to be a design which was originally made for other manufacturing technologies, and the colleagues from DEB made a lightweight approach. They reduced the material. They made a structural mechanical optimization of the part geometry. And other colleagues from Siemens offered one other nice use case demo part. This is a burner part for gas turbines. I think originally what we see on the left is a conventional part. It was I think built up from up to 10 or 12 individual parts, and it was a really complicated process chain, a lot of milling operations and also welding operations. And due to systematic part screening and a redesign, they were able to merge these 12 parts into one part, and this part then finally is 3D printed, and it is a working success story now for the gas turbine area. So we want to encourage you to think about such possible use cases that you might have in your own businesses. And on the other side, I mentioned there is another potential lying in the material that you are able to use. And this is also something that we like to do in our research. We do a lot of material research. Also, we are for sure no material scientists, but we are manufacturing guys. And as manufacturing engineers, it's always important to know about the properties and to know how to influence the process and the material during the manufacturing process. So we're having a lot of different activities where we're looking for new alloys. One of my favorite topic is amorphous alloys, bulk metallic glasses, metal alloys basically, which are which have amorphous microstructure, not a crystalline microstructure, and there we are able to produce really fine and exciting parts for medical technology, but also for other applications. I think there's another example approaching in the next slides. And always what is then important when it comes to new materials is to know about the material properties. And that's also why we can offer a lot of material characterization service for you guys if you are interested regarding density or tensor strength, mechanical properties, thermal conductivity, physical properties. Basically, university, we have a good infrastructure to analyze and to measure the properties that you might be interested into. And also what we see as the main goal for our Lighthouse project is to provide a kind of a knowledge transfer, because we are doing all this research and for sure we are sharing it by writing papers for journals or presenting stuff on conferences, but this might not be maybe the main information channels that you are using for your own business. So we see a big chance from this Interreg project to get a little bit more in touch with you and to present our results and to report on what is today possible with new materials for additive manufacturing or with new adapted additive manufacturing process strategies or new designs for additive manufacturing. So we try to bridge the gap between the academia world and the industry world. And that's why we are doing this workshop and also this webinar today. And to get you a bit more informed what we are doing, the time is limited, so I cannot report everything on what we did in the last month and years. I mentioned that we have this cooperation with the ZBT, the Fuel Cell Technology Center, and there we made some contributions to develop new bipolar plate designs. The colleagues, they made a simulation-assisted optimization of the geometry, and then it came to prototyping, and for the prototyping we were able to print the flow field, the bipolar plates, and also the porous transport layer. And I think also that there's a lot of potential in developing new materials that might be electrocatalytic active for the processes in the fuel cell, but also maybe for the processes in electrolyzers. Another project that we are working on is together with a small startup from the university. Aircode is the name. They are basically working on, let's say, advanced RFID tags. And we produced a shell for placing this RFID tags in the product. This was a nice design study and also some prototypes basically that were printed using our capacities for additive manufacturing. And another cooperation was with another startup from the university. They are ID for us. They are also dealing with RFID technology, but they are developing the reader. And there we developed a reader housing and printed it in a polymer. And there we considered that this material needed to be electromagnetically conductive. And basically we produced this by material explosion additive manufacturing processes. Other projects which are running right now, there are a lot of different other projects. For example, we are doing material tests for industry partners. One partner is developing new alloys for additive manufacturing, and we are then basically optimizing the process to get the demanded material properties. Another project now runs for getting more insight into the robot-assisted additive manufacturing. The students of mine is working on a test bench where we try to use a material extrusion device for polymers in combination with a KUKA robot in order to print much bigger parts for different applications and for different industries. One application might be what we see here. This is a running test for a wind turbine blade. So in the future, we hopefully will be able to print these blades for the wind turbines. And then, possibly this might help to scale up and to increase the development of new shapes for wind turbine blades. All right, and this is what we like doing. And we also, outside of this Interreg project, we did this regularly with different partners. This is basically some references from industry corporations from the last 5 years, and we like to getting in touch with a bigger industry player, but also with a lot of SME companies. And for sure, we cannot report everything what we are doing with industry partners because of IP topics, but in the end, it is always nice to not only look into the academia work, but also getting a bit in touch with the needs and demands from industry. And we have one more research project where we all are already addressing both topics of developing new materials and developing new applications for additive manufacturing. Here we try to 3D print a battery, and this was in the first step one small cell consisting of 2 electrodes, and the advantage here is that we can hopefully be able to print and to manufacture a lot more complicated electrodes, which might be then a good possibility to increase the overall energy density of a battery. And here we modified an existing 3D printer so that we were able to tailor the process parameters and basically the control. And we also made developed some strategies to do an optimized path planning for printing these really fine structured electrodes for the battery. And it turned out that they also really worked. So this is a nice project where we learned a lot of things. And there also industry was involved to determine the properties and to report about the measured capabilities of these electrodes. Another project, what we did, which was originally a fundamental research project funded by the Deutsche Forschungsgemeinschaft, was a project where we optimized and at the end additively manufactured also a tool for polymer dye extrusion. This is a process that basically melts polymer granulates, and then this polymer melt is directed into the tool, and then we are able to produce an endless tube basically of a thin foil, and these are then applications that you see in your everyday life in the supermarket or basically everywhere where you need thin foils made from polymer. And here we were able to develop a totally new design for this melt carrying channels, so that where is it? Here is it. So that the thermal radiological properties of the melt could be improved, and therefore this tool is smaller but also more efficient than the conventional one. And also what we learned during this project is that there's a really high need for surface topologies, especially in the melt carrying channels. So we developed strategies and post processes to optimize the surface structure in these internal channels, and there we are now able to produce really good results with plasma electropolishing and also with abrasive flow machining. And maybe these are some post-processing technologies that might also be helpful for you, because we often notice that the surface qualities that we are able to produce with additive manufacturing is not so good, depending on the process for sure, but there are now available post-processing routes that can offer you really good surface quality near polished. So this was also for me something what I think is really impressive. All right, and then I explained that my favorite materials at the moment are bulk metallic glasses. So what are bulk metallic glasses? These are basically amorphous alloys, and we see in this video what they can do. On the left, what you saw, these are 2 steel balls, small steel balls from GEOS basically, and then we produced a steel plate, and on this side there's a metallic glass, and when we are dropping these small steel balls on the surface, we see that this jumps a bit, and then the jumping is ended, and this is a material obviously which has a really high capacity for elastic deformation. And this is the main advantage basically from bulk metallic glasses. We see when we compare this to steels or titanium alloys, crystalline alloys, we have certain mechanical properties, so yield strength that we know, but when we compare this kind of alloys to iron-based bulk metallic glasses, we see that the strength is doubled more or less. And additionally, the elastic strain limit is 1 order of magnitude higher. So we have the elastic properties of polymers in combination with strongly enhanced mechanical properties. And this is then a really interesting property portfolio for different application. And one application that we are already looking into is to use these new metals and new alloys for producing parts, joints for orthesis. So this is one nice project which is funded from the German SIM program together with Göttinger. They are producing and designing these orthesis for children and for everybody basically. And here we are able to develop a totally new joint structure for improving the mechanical resilience, and additionally to enable a better degree of freedom regarding the movement in this structure. And this structure that we developed here in this project works only for metallic glasses. If we would use a stainless steel here, we would drastically damage the material. We would reach everything which is red is a region where the plastic deformation limit is reached. And so there would be a deformation, and in the long term, basically the material would break. And due to this high mechanical resilience from amorphous metals, we are able to develop totally new structures and to enable totally new functions for the orthesis. All right, so this was then a short overview of what we are doing and what we might offer in the Lighthouse project. And now let's talk a bit more about the limits, what we have with additive manufacturing. I already mentioned it in my introduction, but from our side, I would be interested in what you think, but from our side, we often get the feedback that additive manufacturing is not so cost efficient. And this might be true depending on the application scenarios that you're looking on. So we have really to take a closer look into the boundary conditions on the lot size, on the shape, on the form of the part, and a lot of different other factors are important for assessing the economic efficiency of additive manufacturing. And here, in order to be able to go there, you are, I think, one challenge is to identify the most suitable additive manufacturing technology for your demands. And then one thing which is always often raised by industry partners when we talk to them is that they are lacking a legal or maybe a normative framework like standards. There are a lot of standards already developed, but not everybody knows it. We will come later on to this point. And one more thing for sure is to keep in mind the possibilities to be more resource efficient regarding material and energy consumption, but also to tailor processes, products or process chains, which might be encouraging you to be more sustainable. So this is, I think, something that we could together work on. I would be interested in what's your opinion on this. And just to make clear that there's a lot of different additive manufacturing technology today. This is something that we saw during the last Formnext in Frankfurt in November. It's a big trade fair on additive manufacturing, and every year you see new upcoming processes here. Some years ago, the multi-jet fusion process was something new, more or less a modified laser sintering process, and then we have these material granulate extrusion processes, which are now really gaining momentum at the moment. We have material jetting processes and a lot of different other processes. We do not have the time today to go into every process, but what I want to explain with this slide is that there's still a dynamic going on in terms of development of new processes and new process strategies. Also, a funny thing from my perspective is that during the last 5 years, we are seeing more and more companies who are working with wire arc additive manufacturing. So basically, these are welding processes in combination with an automation of robotics. We might be able to 3D print bigger metallic structures using the established welding technology. Some weeks ago, I visited the BMW facility in Munich, and they are now about to build up production capacities for wire arc additive manufacturing for automotive parts, really. And they did a lot of qualification, and they have the mechanical properties that they are aiming for. And this is a business case now for them. So it's a new emerging, not so new technology, but it's a new field of application. So I want to tell you with this that there's a lot of dynamic going on, and it is it might be interesting to be a bit involved, or to have a look on what's going on and what are the different technologies offering you for your application. Yeah, and basically then you need to have a small insight in what are the strengths and weaknesses of the different technologies. So if you compare it for metal additive manufacturing, we can qualitatively make a small assessment that the powder bed fusion technology, for example, where we're using powder beds or metal powders and laser or electron beam to melt layers, layer by layer. We see that the market is already established, that the mechanical qualities are quite good. We have a good accuracy, but there's some optimization potential in the field of energy consumption or production speed, especially. And when it comes to binder jetting, this is a technology where the production speed is strongly enhanced, but only for certain geometries and certain parts. And there's not so many data already known about the mechanical quality, and the market is quite small at the moment. So it depends always on the technology and the processes that we are looking on, and this is still ongoing. And I'm really confident that in the next 10 years, this might maybe look a bit other shape. But yeah, this is the state of the art what we have right now, and this is the things that we might be able to talk about in the next terms, or maybe in the project when you're interested. And yeah, this is the process-related thing. And then from my perspective, there's a design-related thing, which is important for additive manufacturing. This is what we call design for additive manufacturing. So here, the main task is to think about the limitations from the manufacturing process and the process category. Are we talking about powder bed fusion process, or are we talking about material extrusion? So we have totally different demands on the design. And one thing which is really important is, if we think about a manufacturing ready design, we should also always think about how can we optimize the function of the product or the part, and how could an optimization of the design be able to make the manufacturing process easier, but also be able to raise some added values in the application of the product. And this is totally different for polymers or for metals, and for sure also totally different for different additive manufacturing processes that we are looking at. So there are standards now coming up more and more, international standards where guidelines are more or less established in the first round. So what are do's and don'ts if you're designing a feature for powder bed fusion, or if you are designing a feature for material extrusion processes. So there's already knowledge available, but not everybody knows it, where to find it, and not everybody knows it for, let me say it another way around. It differs a lot in respect to the processes that we are talking about. And if it comes to new processes, these guidelines are not yet established. But in the end, we are trying now to encourage everybody to get a bit more involved into this guidelines, that we might be in the future able to be able to do something like a welding conform construction, or a forging conform construction that we are new for conventional processes. So this might be also available in the future for additive manufacturing. Yeah, and if we don't considering these design guidelines, there might be some process error occurring, and this is also true and still possible. And I always, when I go to trade fairs or conferences, nobody talks about the errors that are appearing in the process. But this is what we do in our research. During my PhD, I made a systematic screening experimentally for provoking different melting processes or for provoking geometric deformation, and I analyzed what was the origin of this process error and how could we optimize the processes to avoid these kind of errors. And yeah, also this might be something that nobody shows you on a trade fair or on a conference. Depending on the material and on the solidification conditions, we have a severe cracking for some materials. This was a cobalt-based material, a new material for sure, and this yeah was something this should only demonstrate you there are challenges that you might not be aware of when you make your first tries. And what we want to avoid is that you guys are buying a, let's say, a metal 3D printer machine for 4 million euros. You're purchasing the material and then you want to produce something, and then something like this turns up. This should be avoided. Here, this for sure can be avoided by selecting the right material and by optimizing the process parameters. And here, in this certain case, we had a lot of residual stresses during the melting. So we needed to heat up the process chamber. We needed preheating, like we also know it from conventional welding technologies. And we are now about to build up more and more knowledge how to avoid this kind of process errors and crackings and other stuff which might be yeah, not so good for you in the end. And we are not the only ones who do this. This is also a good news that I mentioned it already, that there's a legal and normative framework which grows and grows. And also the positive thing is that this is right now happening around the world. There are different national agencies from our side. For sure, the DEAN is something, yeah, well-known institution who does a lot of standardization work, but also the VDI. That's also where we are active from the chair of manufacturing technology. We are writing standards for VDI and also for DEAN committees. And we have the ASTM who does a lot of work, and we have on the ISO level technical committees. This is the TC 261, and the good thing is that every national standardization organization is now working together, and we have several agreements where experts from around the world write standards for different topics on additive manufacturing. And the result is what we can see here. There are now a lot of standards already being published. I think around 30 standards are available. And these are all DEAN, EN, ISO, ASTM standards. And the standard family, so to say, is the 52 and 900 series. And there we have defined general principles on the fundamentals and the terms, the vocabulary that we're using, the requirements for the parts, for test artifacts, for feedstock materials, how to quantify the quality of metal powders, for example, and for sure also some design requirements and guidelines. And this is something which is already available and which might not, yeah, maybe this is not so known in the industry right now. And honestly, it's also a bit hard to get the overview because there are so many standards now being developed. And even for me, as somebody who's involved in certain standardization committees, it's hard to always to be up to date what the colleagues in the other group are doing. So there's a lot of dynamics there, and but it's for sure possible to keep the overview. Yeah, and for sure, one thing which is important is how to find out how to produce parts in a sustainable and resource efficient way, which might then be in the end also beneficial for the economical aspects of the process. So we need to have a look when we are developing this new process change or when we are developing new products. It might be helpful to take a look on the material usage that we need, also for the energy consumption for the whole process chain, not only the manufacturing, but also the post-processing, which is often a showstopper. For example, if we go for powder bed fusion parts from metal, so selective laser melting processes, then we often have the need for support structures. And if we have a sophisticated complex geometry, which is full of support structures necessarily for the process, and then we would have to do an extensive post-processing work. And this could be then a showstopper in the end. So we need always to look on the whole production chain from the design to the post-processing and to the usage in the application. And there it is important to see and to identify the potentials for the recyclability, also for the material waste that might be there, and also for sure for the possibility for reusing materials. All right, so, and that basically was in the end what I wanted to present. I hope that I could give you some insights into what we are doing, what we could maybe offer for you. And now I would be really excited to see what do you think about these topics. What challenges do you see? I think I have the feeling that the most suitable AM technology is not so clear for everybody. And I also could assume that you are interested in how to make it more cost efficient. Maybe you want to know something more about the normative framework, about the possibilities to increase the sustainability. And so I would like to open the discussion and to thank everybody for listening. And let's see if there are some questions. Thank you.
Yeah, thank you very much for this very interesting and insightful presentation. So if you have any questions, you can raise your hands. I found this raise your hand function in Reagieren, so reactions, and then you can raise your hand, or you can just type your question into the chat and I can read it out if you prefer. So yeah, I would say you have a very broad and impressive scope. So you have the overview about the legal and normative framework on the one hand, and you have the production line, software, hardware, and also materials for various application fields. I think that there might be a lot of ideas, for example, decentralized production of spare parts. You also mentioned the spare parts. Maybe it's also combined with reverse engineering. Are these also topics where you're in, for example, scanning part and, for example, reconstructing it? I heard that for vinyl, these production lines for vinyl for this is very, the machines are old and it's hard to reconstruct because they are just physical plans on paper. So you're also working on this. If you have a very old machine that you can do reverse engineering and produce spare parts.
Yes, absolutely. This is a really interesting topic, and this is mostly also something which works economically and technologically, for sure. But you need to have the possibilities and the capacities to do this 3D scanning. But nowadays, it isn't for sure not so easy. But you always may have to do some redesigning and re-engineering of this point cloud that you are getting with your 3D scan. But the algorithms, the software, and also the scanning devices are better and better, are getting better and better year by year. Depending on, for sure, always on your demands, on your accuracy that you want to have, it is feasible, and often it is a working business case to do the scanning and the remanufacturing by additive manufacturing. Because we once had a project where we did this for the automotive industry. There was a part from an old timer. I think this was an Aston Martin or something like this. And there we did this remanufacturing and re-engineering approach. We scanned the part, corrected it, and designed it in order to fix the issues that broke it. And then we 3D printed it, and it worked out. And there was no need to develop certain tools for the casting or whatever. So this is a good application from my point of view.
Yeah. For example, yeah, you also shown several times that you are able to produce very complex structures. So on the other hand, I would even say, okay, if you can print a spare part, you can even improve it. For example, with
Yes.
some
Yeah.
tubes where you can put sensors in, for example, for predictive maintenance and so on.
Yeah.
And you also said, okay, about the properties of processes and materials and so on. Is you told also, something about the regulation, the standards, legal, normative framework, and so on. Is it easy for a company to print spare parts? Because you say, yeah, there is already a normative framework. Because if I decide it might be useful, I have several plants, and it might be useful to print a screw,
Mhm.
but you need a certificate for this. So is it easy or is it hard?
It depends on the market, basically,
Mhm.
and on the demands for the regulation. So often where it works quite well is when it comes to housings of polymer, maybe.
Mhm.
So simple structures and this often there the demands from the regulation side are not so high. We once had, not a project, but interesting conversation with one of our partners who did this for electronic housings. And there, the possibility to produce polymers which are flame retardant was important for the certification. But then you need to get the insight from what is the material properties that is needed and demanded, and then you can go to the regular certification process if you wanted to do so. We are in contact with some colleagues from Daimler. They have a subdivision Daimler buses, EvoBus, and there they are doing this in a bigger picture. They are producing spare parts for buses, which are used, basically in your city for transporting you from A to B. And they did all this certification for their certain field. Same thing is approaching for the aircraft industry or automotive, and basically in the end, it is not so different to conventional manufacturing. So
Mhm.
you have to prove that the material properties are there, and then you can basically include your workflow into your certification framework. But for sure, if you are new to this kind of manufacturing technology, this might not be so easy to do the certification because there's lot of money that you have to spend. In this case, you could work together with specialized contract manufacturer who have the certification. So this is also for sure a really relevant point
Mhm.
and might on the first side be a showstopper for many applications. But there are ways depending on what are the demands on regulation or your material properties that you have.
Mhm. Yeah. I don't like showstoppers, but I would say, therefore, we are here because I would say another point could be to get in contact with you for the first questions. What do you have to do if I need this certification and so on? Because as you already mentioned, if it's possible to print spare parts for planes, for example, sometimes it's hard because flights are delayed just because of small parts. But if you can print them,
Mhm.
you don't have them. You don't need to have these parts lying somewhere. You can print them. Whatever you need, you can print it. So I would say this is a very good vision.
Mhm.
For the optimization of your processes, I'm just a bit curious. What is the impact of artificial intelligence? If you print something and you had these pictures where something didn't work well, is it
Mhm.
also that artificial intelligence might be used to optimize processes? Maybe the robot was too fast or the laser was too hot. I don't know.
Yeah, yeah. Mhm. For sure, this is a mighty tool also for us in the manufacturing area and also for additive manufacturing. Because from my experience, one thing which is special about additive manufacturing is that we have a lot of parameters who are important for improving or determining the properties in the part. And also indirectly to determine the quality and the stability of the process. And therefore, a lot of machine providers, manufacturers for additive manufacturing, they did some work on process monitoring. So we have this layer by layer process, and basically we could inspect every layer that we are producing by process monitoring and gain data. And then the challenge is to correlate this kind of data with our material properties and with the process parameters. And this is not easy. There are really, really many combinations and many thinkable relations. And I think that often when we do this, when we try to optimize the process, we are doing this empirically and experimentally. And here, artificial intelligence might really be helpful to improve our ability for process monitoring and process control in the end. But this is basically, as I like to say, this is the holy grail, one of the holy grails of additive manufacturing. A lot of groups and researchers work on this for years, but this is not yet finished. There's a lot of work still to do, and we have to learn and to train a lot. And for sure, if it comes to machine learning, this might be suitable for one certain material, for one certain application, one certain machine. And the possibility to transfer this kind of model to other circumstances is not so easy at the moment. So I think we need some time to get more confident to use these possibilities of AI in additive manufacturing.
Yeah, I see. Because I would say this is this would be another thing which would very suitable for SMEs, for example, because they need the screw. They don't need the knowledge of additive manufacturing, because this is just the tool for a product. So if you have a process or a system which might support you in optimizing the process, could be useful. Okay. By the way, are there any other questions? I don't see questions in the chat, so maybe you can just unmute yourself if you have any questions. I think we are a pretty small round. While we are waiting, I have another question. You told you visited BMW, so I think they are printing bigger structures. But you have also shown one slide with a bipolar plate. What are the minimal structures? Because bipolar, it's like a tin foil with very precise ribs on it, structures.
Yeah, this is depends on the material, on the process, but we are able to be as accurate as 0.1 millimeters in the end. I can show you. Funny thing, I have some bipolar structures here. These are looking like this. So I don't know if you see it. So we are able to print these fine channels, and if we are applying the right post-processing technology to it, we are also able to tailor the surface quality in a way which is interesting then for the bipolar plates. But for sure, due to the process principles that we are using when we are working with powder particles, as in the powder bed fusion technology, we are also always limited in basically on the particle size distribution. So if we are using 100 micrometer particles and using a laser beam diameter of 100 micrometers, then we cannot be better than 100 microns, for sure.
That's logical. Okay. Because this is also one of the innovation projects within Manufacturing NextMaterials, where they are printing filters for air purification. So this is also very impressive because, it's a filter and we are printing. So, yeah. Okay. Do you have any further questions?
Yeah. So if not, I don't know if it's planned to.
There's a question.
Yeah.
You mentioned the various standards. If suppliers adhere to the standards, how reproducible is the production of components between different suppliers, in your opinion, today? Do you have any experience in this area?
All right. So let me see if I understand it right. All right. Yes. So I see. This question addresses the reproducibility, which is for sure not on this high level that we are used to when it comes to, let's say, milling technologies. This kind of technology have decades of years where we started earlier to qualify and to optimize it. So, if we take everything into consideration what is known about the processes, and if we certify the processes and the materials and the machines that we are using, then we can limit basically the scattering of key values that we are measuring to a really small amount. And this works for the in really high regulated industries like the medical industry or the automotive industries. They are bigger and also smaller companies manufacturing parts which are then part of the gas turbine for the airplane. And there it is possible to meet these regulations and to be reproducible in the end. Yes.
Yeah, right. So I would. There's another question. I'm sorry for that. I already started to my screen again. Do you experience AI technology as standardized, reproducible, and safe implementation in additive manufacturing? Or are there any rather arbitrary and random tools?
Yeah. All right. This is an interesting question. And so what is, I think from my perspective, at the moment, it is really hard to standardize AI technologies because it depends basically on the AI method that what you are using. It depends on your data that you use for the training of a model, and I think this is something which is really highly and intensively discussed at the moment, not only for process control or for manufacturing, but also for other parts where AI technology is now really this emerging and disrupted part. So I think I mentioned that to my knowledge, it is not yet established to use AI methods for process control or for the quality management in additive manufacturing. This might be a good perspective for the future, but since we are maybe we are a bit conservative in this direction and really carefully, even especially when it comes to high regulated markets like aircraft industry or the medical industry, I think there are some years to spend on thinking and to gaining more experience, more confidence with the usage of this kind of technology. So my personal opinion is that they will be relevant for identifying, let's say, process errors during the process monitoring, but it's then hard to standardize this. Yeah, and this might be for sure an issue that we have to think about. Yeah.
Yeah, but maybe we find a small consortium with the first test in manufacturing NextMaterials.
Mhm.
Yeah, I think this was the right answer. Okay, do you have further questions?
So if not in the moment, you might have questions. I don't know if you share my contact data or the slides that I
Yeah,
presented. So if there are some questions that you want to email me, just feel free to get in contact. And yeah.
yeah, perfect.
Hmm.
Because this webinar was just the prequel, as we already mentioned, to our workshop we will have on the 4th of February, 4th, so sorry, on the 4th of February in Duisburg. And we also mentioned already, this was the first introduction, that we have prepared a survey, so you can scan the QR code, and I will send it also in a serial mail afterwards. So we would be happy if you can send us your feedback. What are the topics you are interested in? Because based on the feedback of all our guests, we will create the content of this workshop. It will just have a limited amount of seats. Stefan, I think 20 persons you said maximum, because this is a hands-on workshop, so you will get more information, personal information about the topics which were mentioned most.
Yeah.
And I would say another important part within our next steps would be we have these project proposal deadlines in Manufacturing NextMaterials. So if you already have an idea for a project which you would like to start, if you're missing a partner, just contact us. But if you already have an idea, the next deadlines for the proposals is the 16th of January. And then the next call will end on the 9th of April, one day after my birthday. So you have a lot of time for proposals, and we would be happy to get your feedback on the content of our workshop, which we are planning in Duisburg with the RGC by January the 9th, please, because yeah, we still have to plan the content to get the agenda. So these are the next steps we can provide. And as Stefan also already mentioned, we prepared a follow-up email. We are creating a screen recording. I will upload it on YouTube. You will receive the link. You will get the link for the feedback survey. You will get the contact to Dr. Klischinski, to Stefan, and we would be happy to see you in Duisburg and or get in contact, for example, for projects would be very great. So I would say if you don't have any further questions right now, no, I would say we hopefully meet again. Thank you very much. Have a nice season and a good start into the new year. And hopefully we will see you again on February. Thank you.
Thank you, Henrik. Bye-bye.
Bye-bye.
See you.
Thank you.